Hello friends, welcome back in this video session of pharmaceutical analysis. So in this today's session we will be discussing instrumentation of UV visible spectrophotometer. So spectrophotometer is an instrument or it is a device which is used to measure the absorbance of light. Okay, so we have the sample and this sample absorbs the UV light or visible light. So how much amount of light has been absorbed by the sample, and based on that we can record an spectrum which we refer it as UV visible spectrum. So the spectrum is a plot of wavelength on x axis in nanometers and absorbance on the y axis. So when we talk about the UV visible spectrophotometer, so there are basically two types of UV visible spectrophotometer. One which have been used traditionally, we refer it as a single beam spectrophotometer, and nowadays we are using a double beam spectrophotometer. So we will see the construction and working of these two in the next session. Now we will try to understand what are the components of this UV spectrophotometer and what are the roles and functions and working of each of these parts. So when we think of an spectrophotometer, what essential components it will have? So first is the light source. Because it is a spectroscopic technique, so we require the source of electromagnetic radiation which will be emitting the quality radiations. So light source is must. So the light source should emit the stable source of radiant energy at a desired wavelength. Then we require a sample holder which can hold the sample in a particular container, which we refer it as cells or the cuvettes. Then we require the wavelength selector. So preferably we call them as the monochromators, right? So these are the devices which isolates a restricted region of the electromagnetic spectrum used in the measurement. So we know we do measurement at the lambda max of a particular compound. So we have to set that particular lambda max, we have to set only the wavelength which is the wavelength having a maximum absorbance, and we have to restrict all other radiations. So that will be done by the wavelength selector. Additionally, we can keep on scanning a particular sample from the lower wavelength to the shorter wavelength, right? So that is also possible, and then we can record a spectra. Then we also require the photoelectric transducer, that is we refer it as a detector, because the amount of light which is getting transmitted should be sensed by a particular device, we are referring it as a detector, so that we will get the amount of light which has been absorbed by the sample, and then it converts this radiant energy into a usable signal which we can understand, right? So we need a signal processor and the readout system which amplifies and or attenuate the transduced signal and send it to the readout device, such as meter or digital readout or the chart or the spectrum, which we can understand. So these are the 5 essential components of any spectrophotometer which is must in the device. Okay, so we will try to understand the block diagram in a sequential way. So what is the sequence of these components present in the spectrophotometer? So the first point is obviously the radiation source which is emitting the radiation. Then the emitted radiations are usually polychromatic in nature. So this polychromatic radiation will be converted to a monochromatic radiation by the wavelength selector. Then after converting polychromatic radiation into monochromatic radiation, these radiations will be passed through a sample. So we have a sample holder which is usually the cuvettes, and through these cuvettes of specified path length, the radiation which is monochromatic in nature will be passing, right? And then we require the transducer system or the detector system and the preferable readout unit which can give the absorbance or which can give the UV spectrum. So this is a block diagram what we have represented on the top, and at the bottom we have also the schematic diagram of typical spectrophotometer. So you can see the light source which is emitting the radiation in polychromatic way, then wavelength selector converting polychromatic to monochromatic, then monochromatic radiations are passed through the sample, then it will be detected and it will be processed. So this is the generalized idea about the essential components of the spectrophotometer and different parts which are available in the spectrophotometer in a sequential way. So we will now discuss each one of these parts in detail. So first is a radiation source. So there are varieties of radiation sources available in the market, right, and based on what kind of analysis we require, we can select a appropriate radiation source. Nowadays in the modern sophisticated instruments, we have the multiple radiation sources which we can interchange based on what kind of analysis or at what wavelength we require to analyze or record the spectrum. So the ideal properties of any radiation source is it should generate a beam of radiation with sufficient power of energy to detect and measure. If it does not have sufficient power, right, if it is not sufficiently stable, if it is not sufficiently intense, then that will not reach to the detector, the signal may fade out and some instrumental error will be there in the measurement, okay, and that will lead to a false concentration. So we need to have a radiation source which emit the radiation of sufficient power, it should be intense and it should give a stable output for a reasonable period of time. It should not vary with the potential of electric supply. So even though there are minor fluctuation in the energy, still it should emit continuously and intense kind of lines or the spectra in the device. So we have basically two types of radiation sources, right. First is a line source and second is a continuous source. This is also referred as a continuum source of radiations, okay. So what is a continuous source of radiation or light? A continuum source emits the radiation over a broad range of wavelength with a relatively smooth variation in the intensity. So you can see here in the figure, so here we have a intense kind of light, right, and this is quite smooth, right, it is relatively broad, you can see from 650 to 500. So this is relatively broad and covering a broad range of wavelength. So these kind of continuum radiation sources we will be using in absorption spectroscopy, especially UV visible spectroscopy and fluorescence spectroscopy, okay. So for example, we can take an emission spectrum for green LED light which provides the continuous emission over a wavelength range of approximately 530 to 640. So this is a continuum source of wavelength, right, ranging from 530 to 640, which will be relatively broad in nature, okay. So we should keep in mind about the continuum source of light. It is a source which emit the radiation over a broad range of wavelength, okay, over a broad range of wavelength. So that is the first type of radiation sources which we refer it as a continuous source. Then second type is the line source. So we can easily make out from the figure represented here. So when we compare the continuum source was emitting the radiation in a broad way, whereas the line source you can easily make out these are the lines, right. So the radiation is emitted in a very narrow range, okay. So what we can consider in line source, it emits limited number of bands of radiation with limited range of wavelength. Earlier case there was a broad range of wavelength, but in this case the range is very limited and you can observe very few distinct lines. So you can see similar to mass spectra, you are observing here very distinct lines, right, and this is widely used in atomic absorption spectroscopy and molecular fluorescence spectroscopy. So for example, the figure what I have represented here, so you can see CU halo cathode lamp this consists of 7 distinct emission lines. The first two differs only by 0.4 nanometer. So these are the first two which are differing only by 0.4 nanometer and are not resolved in the spectrum. Each emission line has a width of approximately 0.01 nanometer at half of its maximum intensity. So whenever you have or require a very narrow kind of wavelength of radiation, then preferably we should go for the line source rather than the continuum source. So for UV visible and the other kind of fluorescence spectroscopy, we can go for the continuum source, and for atomic absorption, molecular fluorescence, we can go for the line source. So this particular diagram indicates in a tabular way different types of sources which are available, right, and we have seen the first type was a continuum source of radiation and the second was the line source of radiation. So these are the examples of various radiation sources which emits the radiation in a continuum way, right. So you can see the arc lamp, the xenon lamp, then hydrogen or deuterium lamp, tungsten lamp, nursed glower, nichrome wire and glow bar source. These are the examples of radiation sources which emits the light in a continuum way. Then second type is a hollow cathode lamp and the laser beam or the laser radiation, and this tabular form also indicates in which region they emit the radiation. So for example, if I consider the hydrogen or deuterium lamp, so you can see it covers almost all part of the UV radiation. So from 400 near to 400 to 200, it emits all kinds of UV radiations and to some extent in the vacuum UV region, right. Similarly, when we talk about the IR, right, so usually in infrared spectrophotometer we have the nursed glower or the nichrome wire, which is a preferred radiation source in the IR spectrophotometer. Okay. So this diagram or figure gives a clear indication which source is of which type and which source is preferred for what kind of spectroscopy. So if you are going for UV visible, obviously you will go for xenon or hydrogen or deuterium lamp, right, and then the tungsten lamp is also possible. And then when we talk about the line source, hollow cathode lamp or laser beam or laser lamps are used. Okay. So in the UV visible spectrophotometer, usually by default we have two lamps. One is a deuterium lamp which is mainly getting switched on automatically for emitting the radiation in the UV region, ultraviolet region, and the tungsten lamp is used to emit the radiation in the visible region, that is from 800 to 400. Then next point is the wavelength selectors, because whatever measurements we do, most of the times either we go for the photometric mode or we go for the spectrum mode. So photometric mode is a mode in which we know the lambda max of that particular sample, and the spectrum mode is a mode in which we have to scan or we have to find out the lambda max of that particular compound. So for most of these spectroscopic analysis, the radiation consisting of limited or narrow continuous group of wavelength is required. So we require a specific kind of band from the radiation source. So this narrow bandwidth radiation is required for obtaining a linear relationship between your concentration, right, and the response. Okay. So for that you need to filter out or you need to restrict the unwanted radiations and only pass the required monochromatic radiation through the sample, so that you will get a clear spectra, or you will get the absorbance which will be the absorbance of your analyte. So therefore we need the wavelength selectors. So basically there are two types of wavelength selectors, one is a filter and other one is a monochromator. Okay. So we will see what these filters are. So there are again two subtypes of these filters, right. So as the name indicates, they filter out the unwanted radiation and allow only the required or desirable radiations. So we have two kinds of filters. First is the absorption filter and the second one is the interference filter. Absorption filters are used for visible region and interference filters are used for the UV as well as visible, and you can also extend it into a infrared region. Interference filters works on the principle of optical interference. These consist of transparent dielectric material which is sandwiched between the two semi-transparent metallic films. So, the examples of these are calcium fluoride and magnesium fluoride. Okay. So, this is a dielectric material which we can sandwich between the two semi-transparent metallic films. Okay. So, the interference filter, they rely on constructive and destructive interference in order to select a narrow bandwidth of the radiation, and these are constructed as we discussed of transparent dielectric layer which has been sandwiched between the two transparent semi-transparent metallic film and two plates of glass or any other transparent material. So, these interference filters we can use it in UV, visible and IR region of the electromagnetic spectrum. Okay. Now, next is the absorption filters. So, absorption filters, these are the filters which have 100% transmittance over a given range and rapidly fall off to 0% transmittance. The color absorbed in is the complement of the color of the filter. Okay. So, filter absorbing yellow light which is from 575 to 625 nanometer, it will appear as a blue. Okay. So, these are basically made up of the dye in a gelatin, right, and they are complementary colors, right. So, here these are commonly used, these filters, absorption filters are commonly used in the visible region or the work of visible spectrophotometry, right, and often two absorption filters are paired to give the narrow band of transmittance. For example, we can see in this diagram various absorption filters have been represented, right. So, on y axis we have a percent transmittance. So, how much amount of radiation it is going to transmit, right, and then you can see the combination of two filters. So, it is giving a narrow range, right, and when you see only the green filter, it is relatively broad range, and then orange cutoff filter is also available here. So, it is usually you can see on the x axis the range is from 700 to 400. So, that means the absorption filters are useful in the visible region. Okay. We can have a very good simulation available on this particular website, the link is given here. So, you can see this is the absorption filter, right, which is made up of dye gelatin material, and you can see the filtered light, right. So, on the left hand side the unwanted radiation, the colored light has been filtered and only the required light has been passing, right. So, you can select what bandwidth you require, what filter wavelength maximum you require, and then transmission, what kind of transmission you require, which will be going through the sample, right. So, you can just move these left and right and you can adjust it. A very good simulation is given on this particular website, which will help you to understand the concept of absorption filter. Okay. So, you just keep on moving this total bandwidth or filter wavelength, then similarly this will go up and down and it will change the light which is passing or filtering through the absorption filter. So, second type of wavelength selector are monochromator. Okay. So, first type we have seen, they are the filters. Filters can be of two types, that is absorption filter and the interference filter. Okay. So, the second type of the wavelength selector is a monochromator. So, monochromator means literally it is a single in color. So, these are helpful to convert the polychromatic radiation into monochromatic radiation, right. So, that is the role of the monochromator, and it is not practically possible to obtain one wavelength, rather a narrow range of wavelength which we consider it as a band pass is selected. So, there are two main choices of monochromators, right. Again we have two subtypes of monochromator, prism monochromator and diffraction gratings. Okay. So, the prism monochromator was the original component in most of the previous spectrophotometer, but nowadays the prism monochromator have been replaced to high extent with the diffraction grating monochromators, okay, because of the preciseness, accuracy of the filtration. So we can see in these diagrams, you can see here these are the prism monochromators. So polychromatic light is passing through this prism, then it will get diffracted, it will be dispersed, right, and then we have the exit slit. So these exit slit will be focusing only a particular wavelength of light, okay, and then we have a diffraction grating which is nowadays popularly used. So it has a grooves on these this thing surface, and then when you pass a white light, it will diffract only a required wavelength of light. So these grooves, diffraction gratings, can be moved in a particular direction so that we can get the required colored light or the required wavelength of light, okay. So monochromators, wavelength selectors that can continuously scan a broad range of wavelength. So when we don't know the lambda max of a particular compound, what we need to do, we need to take a sample of that and then make a dilution, and then we have to scan the sample throughout the UV and visible radiation. So we will start the scanning from 400, let us say if you are doing in UV region, you can start from 400 to 200. If you are doing in visible region, you can start from 700 to 400, okay, or you can scan the whole range of visible to UV. So you can start with 700 and you can end up with the 200 nanometer, right, and then you will get a UV spectra where you can easily find out where you are observing a maximum absorbance, and then you can intercept on x axis the corresponding wavelength, which we refer it as a lambda max, okay. So scanning varying the wavelength of radiation over a considerable range which you require, and this is used in most scanning colorimeter, the spectrophotometer, including UV, visible and IR spectrophotometers. So this is basically an schematic diagram representing the construction of the grating monochromators, okay. So this is a grating monochromator. You can see they have the grooves, right, for a reflection, and you can see the polychromatic light is coming through the entrance slit, and then it is focused with the help of concave mirrors, and then it is reflecting back on the reflector gratings, and then you can move this reflector gratings, right. You can move this reflector gratings in such a way that the only desired wavelength of light will be exiting or will be coming out through the exit slit, and the other wavelength of light will be restricted in the exit slit, okay. So it has a focal length and it will be restricted there, okay. And the other type we have seen, that is a prism monochromator, right. So this is a construction of prism monochromator. It has an entrance slit, then there are collimating lenses which are focusing the light on the prism, and then prism will disperse the light, and then we have a focusing lens, right. So we can adjust the focusing lens so that only the desired wavelength of light will be getting exit from the exit slit, and the other wavelength of radiation can be restricted. So you can see here lambda 1 is restricted and lambda 2 is allowed to exit from the exit slit. So lambda 2 is a desirable one for our measurement. So similarly we can change afterwards, we can change the focusing lens so that the lambda 1 will be exiting and lambda 2 will be restricted. Same thing we can do it for the grating monochromators also, okay. So this is a typical monochromator design by using the grating monochromator, okay. So it consists of the diffraction gratings, that is the dispersion element. So these are the diffraction gratings, and this actually have the grooves on the top surface. So scanning is accomplished by rotating this grating. So we can keep on rotating this grating, right. So when we do the scanning in the spectrophotometer, actually what is happening, the diffraction gratings are moving so that a particular wavelength is passing at a particular time, and then the other wavelengths will be restricted. So in the diagram what we can see that incoming light enters the prism and different wavelength are refracted back into the different amount. So in this example you can see the light source emitting polychromatic radiation, it has been focused through the entrance slit on the collimating mirror, and then collimating mirror focusing the light on the diffracting gratings, the light will get diffracted on the focusing mirror, and then you can see only in this case the green light is coming out of the exit slit, whereas the purple and red light, that is lambda 1 and lambda 3, have been restricted here, right. So if I rotate this diffraction grating in such a way that I can allow lambda 1 to come out from the exit slit and lambda 2 and lambda 3, that is green and red, I can restrict it. So this can be done very easily in the spectrophotometer, and you can scan your sample in the entire visible and UV range, that is from 700 to 200 within a fraction of time, right. So within a half minute probably you can complete the scanning of your sample in the entire visible and UV range, and then you will record an UV spectrum which will be helping you to find out the lambda max or the concentration, right. So this is the working and operation and the construction of these grating monochromators. So same has been discussed here, so you just go through these sentences which will help you to understand in a better way the grating monochromators. So these grating monochromators can be of two types again. So here you can see in the diagram, so this is the first type, it is referred as the T.Y.B.Pharm instrument, where it uses one large spherical mirror and one plane diffraction gratings, okay. And then we have this second type of grating monochromator, that is the Journey Turner grating monochromator. So it consists of two concave mirrors and one plane diffraction gratings, okay. So you can see this is a one concave mirror and this is another concave mirror, and we have the gratings, the diffraction gratings. So we can keep on rotating this diffraction gratings to get a particular wavelength of light which should exit from the exit slit. Similarly here again you can keep on rotating the grating, these gratings, right, and this is how it has been directing towards the grating plates and then towards the exit slit. Then next is a prism monochromator. So we have discussed about the grating monochromators, right. Now we will talk about the prism monochromator. So prism can be used to disperse the UV visible and IR radiation, and the material of construction differs depending upon the wavelength of the region. So you can see in this figure the light is coming, right, and then when it passes through the prism it will get diffracted. So this is referred as a dispersion angle, and the light has been dispersed into, in this case, 7 colors, right. So it into a different kind of wavelength here, okay. So there are again two subtypes of prism monochromators. One is referred as a cornu prism. Now this cornu prism, it is 60-degree prism of a single block of material such as the quartz, and this can be made up of cementing two 30-degree prism together, first from right headed quartz and second from the left headed quartz. Then second type is a litroprism, and it has a 30-degree prism with the mirrored back. So refraction in this two type of prism take place twice, okay. So this is the construction of the cornu prism and this is the construction of the litroprism. So in short, when you take the two litroprism together, right, and when you combine, that will form a cornu prism, and the second is a litroprism. So this is the litroprism which has a 30-degree prism, whereas the cornu prism, it is a 60-degree prism, right. Or you can take two 30-degree litroprism and cement them together, that will form a cornu prism. Then in generalized way we should also discuss the gratings, right. So these are the gratings which has a grooves on it, and this is actually helping to select a particular wavelength of light. So broadly there are two kinds of gratings, one is a transmission grating and other one is a reflection grating, and this reflection grating are very commonly used in instruments. So master grating, which consists of hard optically flat polished surface ruled with suitable shaped diamond tool to a large number of parallel and closely spaced grooves, which will help you to select a narrow bandwidth of the wavelength. So UV and visible region contains from 300 to 2000 grooves per mm, and for IR it range from 10 to 200 grooves per mm. Okay, so that is the material and construction kind of gratings based on what kind of purpose you have, whether you are using in IR or UV spectrophotometer, and the construction is relatively tedious and time consuming and also expensive because of the finer grooves. Okay, so this is all about the gratings. In the next session we will discuss about the sample holder and other parts of the instrument. Thank you for watching it.